I want you to imagine, just for a second, that you're trying to thread a needle.
Okay, sounds hard enough already.
Right, but you're not sitting at a quiet, well-lit desk. You are riding a roller coaster,
Oh, wow.
and you're completely blindfolded. And just to push this whole scenario into the realm of the absurd, you are attempting to do all of this in the middle of a freezing, howling blizzard.
Well, I mean, the physical probability of a human being actually pulling that off drops to effectively zero.
Yeah, exactly.
Biology just cannot process that level of chaotic sensory input and, execute a micromillimeter physical action all at the same time.
And yet that chaotic, blinding, violently turbulent scenario is basically the baseline operating reality for a modern, advanced, unmanned aerial vehicle.
It really is.
When a UAV navigates through a hostile, electromagnetically jammed airspace, it is literally flying blind in a blizzard while trying to thread a mathematical needle.
That's a great way to put it.
So today, we're taking a massive deep dive into the source material that explains how these machines actually survive that nightmare. We're looking exclusively at the brain and the nervous system of modern drones.
Right, which engineers refer to as the GNC system.
Yeah, the GNC. So that stands for
Guidance, navigation, and control. They are the three fundamental pillars of autonomous flight.
Okay, so let's break those down really quickly for the listeners.
Sure. So if we break those down into their core operational questions, guidance is basically the drone's strategic mind asking, based on my current parameters and mission, what is the safest, most efficient three-dimensional path to my target?
Right. Like, how do I get from A to B without hitting a mountain?
Exactly. Then navigation is the spatial awareness system. It's asking, where am I located right now, down to the centimeter, relative to the Earth and any obstacles.
Okay, and then control.
Control is the physical translation layer. It's the system asking, how many micro adjustments must I make to my wing surfaces and, motor RPMs in the next millisecond to physically execute that path?
In the next millisecond. That speed is just wild. I want to frame why you, the listener, should care about this.
Definitely.
Because whether your primary interest lies in the future of aviation or the rapid evolution of artificial intelligence, or you just find it fascinating how machines are achieving levels of autonomy that seem like pure science fiction, understanding GNC is essentially the skeleton key.
It really is the foundation of it all.
It strips away the magic. You
Yeah.
know? It shows you the raw, paranoid engineering that allows a machine to thrive when literally everything in its environment goes wrong.
And the environment is the crucial context here, right? We are not analyzing the architecture of some consumer hobby drone that you fly over a sunny park.
Right. This isn't a toy.
No, not at all. The sources we are diving into deal with highly contested airspace. I mean, we are talking about altitudes where the atmospheric temperature plunges to like minus 40 degrees Celsius.
Crazy.
Beyond freezing. And where hostile actors are actively deploying directed energy or electronic warfare to completely blind the drone sensors.
Plus the severe aerodynamic turbulence that's constantly threatening to just tear the chassis apart.
Exactly. So in the realm of advanced aerospace engineering, building a system for that environment requires eliminating a concept that makes engineers physically shudder.
Which
The single point of failure.
Right. Because if one wire snaps or a single microscopic silicon pathway in the chip overheats,
Yep.
the entire multi-million-dollar aircraft becomes a very expensive falling brick.
Precisely. So the entire architecture of a modern UAV GNC system is mathematically constructed to ensure a single point of failure just cannot exist.
It assumes things will break.
It assumes a component will fail. It assumes its sensors will lie to it. The system is fundamentally designed to survive its own internal death.
That is so wild. So let's crack open the skull of this machine and look at the brain itself.
Let's do it.
The sources dedicate a massive amount of technical detail to hardware redundancy, specifically something called the Triple Redundant Flight Control Core.
Right. You might see it abbreviated in the literature as TMR, or Triple Modular Redundancy.
CMR, got it. So to put it simply, this machine doesn't have one brain. It has three.
Three completely independent flight control cores, and they aren't configured in a primary backup relationship, where one is asleep until the other fails.
Oh, so they're all awake at the same time.
Yes. They are running side by side, analyzing the exact same data streams simultaneously, operating on deterministic real-time operating systems.
Which the industry calls an RTOS.
Exactly, RTOS.
The word deterministic feels like the hinge this entire system swings on, doesn't it?
It's everything.
Like if I open an application on my smartphone, the time it takes to load is variable. If I have background apps running, it might take a full second.
Right, or if you just rebooted the phone, it might take 50 milliseconds.
Yeah, exactly. My consumer phone operates on probabilities and, best efforts.
But a flake controller operating on best efforts would result in a catastrophic crash.
Just boom, out of the sky.
Basically, yeah. In a deterministic system, a calculation is mathematically guaranteed to take the exact same amount of time every single time, down to the specific microsecond.
Wow.
There is no buffering. There is no waiting for memory allocation. If the drone is hit by a massive thermal updraft, the control layer has to calculate the exact corrective motor speeds in under 5 milliseconds.
5 milliseconds.
If the operating system gets distracted for, say, 6 milliseconds, the aircraft loses its aerodynamic stability.
So you have these three brains running these hyper-rigid deterministic loops, just constantly parsing sensor data and calculating the drone's attitude in three-dimensional space.
Yes, and they don't just calculate in isolation. They have to come to a consensus.
Okay, how does that work?
The sources detail this voting logic handled by a dedicated hardware arbitration chip.
Ah, a voter chip.
Exactly. It's a literal high-speed democracy inside the circuit board. Every single microsecond, Core A, Core B, and Core C solve the exact same massive matrix of flight equations.
Essentially asking, what should our pitch angle be right now to avoid crashing?
Right, and they submit their final mathematical answers to this voter chip. The arbitration chip acts as an entirely impartial judge.
Okay, so under optimal conditions, Core A outputs a pitch of 5 degrees, Core B outputs 5 degrees, and Core C outputs 5 degrees.
And the voter validates the consensus, passes the command to the motor controllers, and the aircraft continues its flight.
Simple enough.
But consider the reality of the stratosphere. The drone is operating at 20,000 feet where the atmosphere is incredibly thin.
Right.
Because there is less atmospheric protection, the circuitry is highly vulnerable to cosmic rays.
Wait, cosmic rays, like high-energy atomic fragments from deep space?
Yes, exactly. So imagine a microscopic particle from a supernova strikes the silicon of Core B.
Just bam, right into the chip.
It strikes the silicon and causes a physical bit flip in the processor's memory register. A tiny electrical charge literally changes a 0 to a 1. In an instant, Core B's mathematical output is corrupted. It suddenly insists the drone's pitch should be negative 90 degrees.
So it's screaming at the motor controllers to execute a lethal nosedive straight into the terrain.
But because of the voting logic, Core A and Core C are still isolated from that cosmic ray. They are still outputting the correct 5-degree pitch.
Ah, I see.
The arbitration chip looks at the three inputs, immediately flags Core B as a massive statistical outlier, and mathematically outvotes it.
So Core B's fatal command is just quarantined and ignored.
Yep, and the drone maintains perfect stability. The machine experiences a severe brain injury, diagnoses it, and ignores it in a fraction of a microsecond.
That is incredible. I understand the brilliance of the voting logic, but there is a massive structural vulnerability here that the sources seem to anticipate.
I think I know where you're going with this.
Right, because if I have 3 exact clones of a brain running the exact same software code, compiled on the exact same hardware architecture,
Yes.
what happens if the threat isn't a random cosmic ray? What if the threat is a fundamental architectural flaw,
Ah, a systematic issue.
like a highly specific zero-day software bug, or a physical vulnerability to a specific electromagnetic frequency? If you trigger that flaw, won't all 3 brains fail simultaneously?
That's a very real concern.
Because voting doesn't do you any good if Core A, Core B, and Core C all confidently agree on the exact same suicidal command.
You're absolutely right. The vulnerability you just outlined is known in aerospace engineering as a common mode failure.
Common mode failure.
It is the nightmare scenario where a single underlying trigger exploits a shared weakness across all redundant systems, causing a total simultaneous collapse.
So how do they stop that?
To counteract this, engineers employ a strategy that seems almost counterintuitive at first glance. They deliberately ensure the 3 brains are not clones.
Wait, really?
Yes. The source material refers to this as dissimilar hardware or a heterogeneous architecture.
Okay, so they are actively mixing and matching the fundamental DNA of the processors on the motherboard.
They are utilizing entirely different microprocessing paradigms. For instance, Core A might be engineered using an ARM Cortex architecture, which handles instruction sets in a highly specific way.
Sure, ARM is pretty common.
But Core B is built on a RISC-V architecture, which utilizes a completely different physical layout of logic gates and instruction pathways.
Which means they speak fundamentally different physical languages at the silicon level, even though they're trying to solve the exact same overarching flight control problem.
Exactly. The overarching mathematical laws of flight they are executing are identical, but the physical journey the electrons take through the silicon to arrive at the answer is drastically different.
So if a highly sophisticated software virus hits the system,
Or a bizarre compiler error or a specific voltage spike.
right, the probability of it affecting an ARM processor and a RISC-V processor in the exact same way, producing the exact same erroneous mathematical output at the exact same microsecond, is virtually zero.
That's the beauty of it.
I picture this as having a complex astrophysics problem solved simultaneously by, like, a human savant, an ancient mechanical abacus, and a modern supercomputer.
That is a fascinating analogy.
Right, because if all three arrive at the same orbital trajectory, you have absolute confidence in the answer. But if a malicious actor slips a digital virus into the supercomputer, the human and the abacus are entirely immune to it.
Exactly. They won't make the same mistake because they don't process information using the same physical mechanics.
Wow. So the asymmetrical design creates a firewall against systemic logic failures.
It does. However, the paranoia engineered into these GNC systems goes even one layer deeper.
Deeper than dissimilar hardware voting.
Oh, yeah. The heterogeneous voting system is robust, but it still relies on the fundamental assumption that the processors are actually capable of outputting a vote.
Okay, true.
What happens if the power delivery dips for half a millisecond, causing the main processing threads across all cores to entirely deadlock?
Oh, so the system just freezes.
Yeah.
And you can't just pull a drone over to the side of a cloud, wait for the spinning loading wheel to disappear, and perform a hard reboot. Gravity doesn't pause for a system restart.
Exactly, which necessitates the independent watchdog mechanism.
The watchdog. Sounds aggressive.
It is. The watchdog is the ultimate uncompromising failsafe. Think of it as a highly aggressive digital deadman switch.
How does it work physically?
Every single compute unit on the flight controller is tethered to a fully independent, incredibly simple analog-style circuit whose sole purpose in existence is to wait for a heartbeat signal.
So the main processor has to constantly tell the watchdog, I am alive, I am calculating.
Every few microseconds, the processor pulses that heartbeat. If that heartbeat stops, if the processor enters an infinite loop or a thread deadlocks, or it freezes for even 1 millisecond,
The watchdog steps in.
the watchdog does not attempt to diagnose the issue. It does not wait to see if the processor recovers. The watchdog bites.
It bites.
It instantly severs the frozen processor's access to the motor controllers and physically forces a switch to a completely independent backup chip to take over flight authority.
It aggressively rips the steering yoke out of the paralyzed pilot's hands and gives it to the co-pilot before the aircraft even has a chance to dip its nose.
It's a perfect visual, and the speed of that transition is paramount because of a physical phenomenon known as attitude divergence.
Attitude divergence, what's that?
A multi-rotor drone, or an unstable fixed-wing UAV, is not naturally inclined to fly level. It inherently wants to flip over and fall.
Really? It just naturally wants to crash.
Pretty much. Remaining level requires hundreds of microscopic adjustments to the motors every single second.
Oh, wow.
If the flight controller freezes and those adjustments start for even half a second, the drone's physical attitude will diverge from level flight so violently that recovery becomes aerodynamically impossible.
So the watchdog mechanism guarantees that the control loop is never broken, no matter how catastrophic the software failure.
Exactly. It forces continuity.
So if we synthesize this first major pillar, the drone has a profoundly paranoid, triple-redundant, heterogeneous brain that utilizes a democratic voting system and is guarded by aggressive deadman switches.
A very robust brain.
The logic core is virtually bulletproof. But if I take a human with a genius-level intellect, blindfold them, spin them the circle 50 times and tell them to walk a straight line, their perfect brain is still going to send them crashing into a wall.
Without a doubt.
Because the brain is entirely captive to the data it receives from its senses. If the drone's eyes and inner ear start hallucinating, all the ARM and RISC-V processors in the world won't save it.
Garbage in, garbage out.
Exactly. How does the machine ensure the senses feeding that perfect brain aren't lying to it?
That transitions us into the second critical pillar of the GNC architecture, sensor fusion and environmental resilience.
Okay, let's get into it.
Because you're right, the atmosphere at operational altitude is actively hostile to delicate sensing equipment.
Let's focus on the drone's inner ear, the IMUs, or
Yeah.
inertial measurement units. These are the sensors responsible for measuring raw acceleration and rotational velocity, right? They are the only way the drone knows if it is pointing up, down, banking left, or falling out of the sky.
Exactly. Modern aerospace utilizes MEMS IMUs. That stands for microelectromechanical systems.
NEMS.
And the engineering behind these is staggering. We are talking about microscopic, three-dimensional tuning forks and proof masses etched directly into a silicon wafer.
Wait, actual tiny physical structures.
Yes, microscopic moving parts. When the aircraft physically accelerates or rotates, the inertia forces these microscopic silicon structures to bend or vibrate differently.
And then it measures that.
Yes. The chip measures changes in electrical capacitance caused by that microscopic bending and translates it into raw motion data.
The idea of relying on microscopic vibrating tuning forks to keep a multi-ton machine in the air is terrifying when you introduce the cold problem, detailed in the sources.
The cold problem is a massive engineering hurdle. As the drone climbs to operational altitude, the ambient temperature can plummet to -40 or even -50 degrees Celsius.
So what does that do to the sensors?
Extreme cold has a devastating physical effect on silicon. As the material freezes, it physically contracts and stiffens.
Oh, of course.
This alters the resonance and the baseline electrical capacitance of those microscopic structures, resulting in a phenomenon known as temperature drift.
To make sure I grasp the severity of temperature drift, it isn't that the sensor simply shuts down because it's cold, right?
No.
A sensor turning off would be manageable. The drone would know it's offline. Temperature drift means the sensor stays online, but it starts lying.
Exactly. The sensor becomes mathematically deceitful.
Wow.
The drone could be flying perfectly level, parallel to the horizon. But as the freezing silicon contracts, the gyroscope's baseline reading skews. It starts feeding data to the flight controller that says, we are entering a slow, steady bank to the left.
So the flight controller, which is programmed to maintain level flight, receives this false data.
And it reacts.
It thinks the drone is drifting left, so it commands the right side motors to spin faster to correct the bank. But because the drone was actually already level, this correction actually throws the drone into a violent right-hand spiral.
Precisely. The inner ear is hallucinating due to the cold, and the brain acts on the hallucination, driving the machine into the ground.
It is the mathematical equivalent of extreme vertigo. The brain is functioning perfectly, but it's acting on corrupted sensory input.
That's a great analogy.
It reminds me of a sniper operating in a severe winter environment.
How so?
Well, a sniper can possess a perfectly machined rifle, aerodynamically flawless ammunition, and a brain that understands the complex ballistics of windage and elevation.
Right.
But if the sniper's core body temperature drops and they begin to shiver uncontrollably, the crosshairs will bounce violently across the target. To keep the physical instrument mathematically still, the sniper has to aggressively manage their own body heat.
That is exactly what the drone has to do. The sensor requires an absolutely stable physical foundation to output stable mathematical data.
So how do they solve this mechanically?
To solve this, the source material explains that engineers implement redundant IMU constant temperature heating alongside mechanical isolation.
So they essentially build a microscopic heated isolation chamber exclusively for the inner ear.
First, they address the kinetic violence of the environment. The entire IMU array is suspended on specialized mechanical shock absorbers.
Okay, to dampen the vibration.
Yes. These dampeners are mathematically tuned to filter out specific high-frequency vibrations like the high RPM whine of the drone's own motors or the chaotic buffeting of turbulent wind, which would otherwise overwhelm the delicate MEMS sensors.
They isolate the vibration, but how do they conquer the temperature drift?
They wrap the isolated IMUs in active software-controlled heating elements.
Seriously, they just heat them up.
They do, regardless of whether the drone is taking off from a scorching desert runway or plunging through a sub-zero blizzard in the stratosphere. This thermal management system maintains the internal silicon at a constant, highly precise temperature.
Do they have a specific target temp?
Often it's locked right around 60 degrees Celsius. By enforcing an absolutely static thermal environment, the silicon never contracts or expands.
That is brilliant.
They achieve what engineers call zero bias stability. The sensor is physically prohibited from drifting, ensuring it will not lie to the flight controller.
Okay, so the inner ear is heated, isolated, and telling the truth. But the IMU is just one instrument in the orchestra.
Oh, there are many more.
The drone is also being bombarded with data from GPS satellites, atmosphere pressure from barometers, airspeed from pitot tubes, and visual data from optical cameras.
It's a massive influx of information.
How does a computer algorithm take this chaotic cacophony of incoming data, all arriving at different frequencies and with different margins of error, and fuse it into a single coherent picture of reality without becoming totally overwhelmed?
This challenge brings us to the mathematical crown jewel of the GNC system, the extended Kalman filter.
The EKF.
Specifically, the EKF2 or EKF3 algorithms highlighted in the source material. If the triple redundant core is the raw processing power, the EKF2 is the ultimate trust manager inside that brain. It is the core of sensor fusion.
I see the term extended Kalman filter constantly in the literature surrounding autonomous systems, from self-driving cars to spacecraft. The math looks incomprehensibly dense.
It is very complex.
Let's break down the mechanics of what EKF2 is actually doing millisecond by millisecond.
At its core, the EKF2 algorithm's job is to take all these disparate, imperfect, noisy data streams and calculate a single high-confidence state vector.
What exactly is a state vector?
Specifically, it's a 6-degree of freedom, or 6DOF, attitude matrix. It is constantly calculating exactly where the drone is in 3D space, its exact velocity vector, and its precise pitch, roll, and yaw orientation.
But the key word there is imperfect. A GPS satellite signal has a margin of error of several meters. A barometer measuring air pressure can be tricked if the drone flies through a localized pressure pocket or a severe updraft. Even our beautifully heated IMUs have microscopic amounts of electrical noise.
The genius of the EKF2 is that it doesn't just blindly average all those numbers together, it actively manages the concept of covariance.
Covariance. Let's unpack that.
Yeah.
I understand variance is how far a set of numbers is spread out, but in the context of this filter, what does covariance actually represent?
In this context, you can think of covariance as a mathematically rigorous measurement of uncertainty, or a dynamic trust weight.
Trust weight. Okay.
The EKF2 algorithm assigns a real-time trust score to every single sensor based on its historical accuracy and current noise levels.
Oh, so it keeps track of who's being reliable.
Exactly. But the true power of the filter lies in its two-step cycle: prediction and update.
Walk me through that cycle.
Before the sensors even send their next batch of data, the EKF2 uses the laws of physics and its knowledge of the drone's current speed and trajectory to predict exactly where the drone will be and what the sensors should read in the next millisecond.
It essentially generates a mathematical prophecy.
Yes, a prophecy. Then, the actual sensor data arrives. This is the update phase.
So it compares its mathematical prophecy against the raw physical reality reported by the sensors.
And this comparison generates what the EKF2 calls the innovation term.
The innovation term. I love this phrase. It sounds like corporate jargon, but it's actually a brutal mathematical cross-examination.
It really is. It is the precise mathematical difference between the EKF2's prediction and the sensor's actual measurement. Let's apply this to a real-world hostile scenario.
Okay, set the scene.
The drone is flying straight and level. The EKF2 predicts the altitude should remain constant, but suddenly the drone flies into a violent rainstorm and water is physically forced into the barometer's intake port, clogging the sensor.
Because the barometer relies on measuring ambient air pressure to determine altitude, the clog causes the pressure reading inside the sensor to skyrocket or plummet artificially.
Exactly. The barometer suddenly starts screaming at the flight controller. The air pressure is changing radically. We are in a sheer vertical dive, losing hundreds of feet per second.
But the other sensors disagree.
Right.
The GPS is reporting a stable altitude. The heated IMUs are saying, I measure zero downward physical acceleration.
The EKF2 looks at this massive conflict. It calculates the innovation term for the barometer and realizes the delta between the prediction and the barometer's measurement is astronomically high, completely outside the statistical standard deviation.
The innovation term spikes, and the EKF2 catches the liar.
In a fraction of a millisecond, the EKF2 algorithm dynamically slashes the covariance trust weight of that contaminated barometer data stream down to effectively zero.
Just mutes it entirely.
It structurally isolates the bad data, completely ignoring the barometer, and seamlessly shifts the mathematical burden of maintaining altitude to the GPS and the IMUs.
So the drone doesn't twitch. It doesn't initiate a catastrophic pull-up maneuver.
Nope. It simply mathematically amputates the lying sensor until the data returns to statistical norms.
It is a dynamic trust filter that constantly cross-examines its own senses to ensure it never falls victim to sensory illusions.
That's the perfect summary.
The system can think perfectly, and it can mathematically guarantee its physical attitude is correct. But knowing how you are flying is only half the battle. You still have to know where you are flying.
Which brings us to the third critical pillar outlined in the sources: navigation assurance and the reality of blind flying.
Right. If we look at the ideal scenario first, when the airspace is clear and everything is functioning perfectly,
Right.
how does a modern advanced UAV determine its exact position on the globe?
When operating under optimal conditions, the gold standard for navigation is dual GNSS RTK positioning.
Let's parse that acronym. GNSS stands for Global Navigation Satellite System, which encompasses the American GPS, the European Galileo, the Russian GLONASS. RTK stands for Real-Time Kinematic. Why does an advanced drone need RTK? If I open the Map app on my smartphone, it uses standard GPS to find my location, and it's generally accurate to within a few meters.
A 3 to 5 meter margin of error is acceptable if you were trying to find a coffee shop on foot.
Sure.
But if an autonomous drone needs to execute a precision landing on a small moving naval platform or maneuver through dense urban infrastructure, a 3-meter error means the drone crashes into a steel bulkhead.
Oh, that makes sense.
Standard GPS signals are inherently degraded as they pass through the Earth's ionosphere. RTK solves this by introducing a fixed ground base station.
A base station that already knows its exact, mathematically surveyed coordinates on the Earth.
Because the base station knows exactly where it is, it can look at the GPS signals it receives, calculate the exact ionospheric error in those signals in real time, and broadcast a continuous correction data link up to the flying drone.
Okay, wow.
By applying those corrections, the drone achieves centimeter-level absolute spatial positioning.
Centimeter-level accuracy while moving at hundreds of kilometers an hour is a staggering engineering feat. But the source material specifically emphasizes dual GNSS RTK.
Yes, dual.
The drone is carrying 2 separate RTK antennas. If you already have centimeter-level accuracy with one antenna, why bear the weight and computational cost of a second one?
The necessity of the second antenna reveals a fascinating vulnerability in traditional aviation.
What is it?
The second antenna is not primarily for redundancy and positioning, it is to solve the problem of heading.
Heading, like which way it's pointing.
Exactly. By placing 2 highly accurate RTK antennas a fixed, known distance apart on the drone's chassis, the flight controller can calculate the precise geometric vector between those 2 centimeter accurate points.
Oh, clever.
This calculation provides the drone with a highly precise 3-axis heading.
But aircraft have used electronic compasses magnetometers for decades to determine their heading. Why abandon the compass?
Because a magnetometer relies on measuring the Earth's ambient magnetic field, and magnetic fields are incredibly fragile and easily distorted.
Really? How so?
If an autonomous drone flies close to high-voltage power transmission lines, or over a massive deposit of ferrous metal like a steel suspension bridge, the local magnetic field is warped.
So the compass gets confused.
Furthermore, in contested environments, adversaries deploy directed electromagnetic weapons designed specifically to fry or confuse magnetic sensors. If the compass is scrambled, the drone loses its orientation and spirals out of control.
The dual RTK setup entirely bypasses the Earth's magnetic field. It calculates its heading using purely geometric satellite data.
Exactly.
You could fly the drone through a localized magnetic hurricane, and its heading would remain mathematically perfect.
It creates total immunity to magnetic interference.
The logic there is brilliant. But it leads us directly into the massive, unavoidable elephant in the room regarding modern conflict and autonomous flight.
I know what you're going to ask.
The entire dual RTK system, as beautiful as it is, relies entirely on listening to faint radio signals from satellites orbiting 12,000 miles above the Earth.
Yes, it does.
In modern warfare, adversaries deploy massive truck-mounted electronic warfare platforms that can flood the GPS frequencies with overwhelming radio noise.
Jamming.
We constantly hear about GNSS-denied environments. If the enemy jams the spectrum, the RTK correction link is gone. The satellite signals are gone. The heading is gone.
Right.
Does the multi-million-dollar drone just drift helplessly with the wind till it crashes?
Historically, yes. A sudden loss of GPS would trigger an immediate abort, where the drone would attempt a sloppy emergency landing or simply drift into terrain.
Not ideal.
But the GNC systems detailed in these sources are engineered specifically for this nightmare. When the satellite signals are jammed, the EKF2 algorithm instantly recognizes the loss of data and seamlessly switches the drone into a fallback navigation mode known as dead reckoning.
Dead reckoning, powered by visual odometry and sensor fusion. It evokes images of 18th century naval captains navigating wooden ships through heavy fog without a view of the stars.
The fundamental concept is exactly the same, just executed at the speed of light.
Okay, explain how it works.
Dead reckoning means calculating your current unknown position by taking your last known confirmed position and mathematically advancing it based on your continuously measured speed, heading, and elapsed time.
So the drone says, I knew my exact centimeter level coordinates 3 seconds ago, right before the jamming hit. And my heated IMUs tell me I've been accelerating north at 100 kilometers per hour for those 3 seconds.
Exactly. The math seems simple enough.
But IMUs, even perfectly heated ones, accumulate microscopic drift over time. You cannot dead reckon purely on inertial data for long distances without the error compounding until you are miles off course.
You're spot on. The inertial data alone is insufficient. The drone needs an external reference to anchor its math.
So where does it get it if the satellites are jammed?
This is where the drone turns its own onboard local sensors into a localized internal satellite system. The sources specify the integration of a lightweight 3D LiDAR scanner and high-resolution optical cameras, continuously mapping the terrain directly below the aircraft.
Explain the mechanics of how a camera helps a drone navigate when it is completely isolated from the outside radio world.
The flight controller runs a highly complex algorithm known as visual inertial odometry, or VIO. The camera looks down at the Earth and identifies specific high-contrast visual features, the jagged edge of a rock formation, the corner of a building, or even a unique pattern in a dirt road.
Okay.
As the drone flies forward, that visual feature moves across the camera's field of view.
So the algorithm is tracking the exact speed and direction that those pixels are sliding across the camera sensor.
It is essentially reading the visual texture of the ground like Braille.
That's so cool.
By mathematically analyzing how fast hundreds of these visual features move across the pixels frame by frame, and fusing that optical flow data with the high-frequency physical acceleration data from the IMU, the EKF2 can calculate the drone's exact velocity and trajectory relative to the Earth's surface.
That completely bypasses the need for external radio waves. The drone is creating a self-contained reality.
Furthermore, the LiDAR scanner is continuously firing millions of laser pulses at the ground, measuring the time it takes for the light to bounce back to create a real-time 3D topographical elevation map of the terrain.
And what does it do with that map?
The GNC system compares this real-time laser map against preloaded digital elevation models stored in its memory banks.
So it is matching the mountains it sees with its lasers to the mountains it has memorized in its database.
Exactly. The drone is flying entirely deaf and blind to the external radio world. The jamming environment is absolute.
Wow.
Yet by fusing the optical flow of the camera, the topographical data of the LiDAR, and the physical inertia of the heated IMUs, the system can maintain a navigational drift error of less than 10 meters over flights spanning many kilometers.
Less than 10 meters of drift without a single ping from a GPS satellite.
It guarantees the drone maintains the spatial awareness necessary to autonomously navigate out of the jamming bubble, complete its mission, or execute a safe, blind landing in hostile territory.
The engineering is undeniably miraculous, but this capability introduces a massive, deeply concerning safety reality. Let's ground this in a practical scenario.
Sure, let's hear it.
We have a heavy, autonomous machine flying completely blind to external signals, jammed by electronic warfare, navigating by reading the dirt with lasers.
Yep.
And it is doing this over a populated area or a contested airspace. How does this autonomous machine ensure it doesn't plow straight into a news helicopter, a commercial airliner, or another drone? Flying blind in shared airspace is the ultimate regulatory nightmare.
It is the single largest hurdle in modern aerospace regulation. Aviation authorities will not allow these machines into the sky unless the engineering can mathematically guarantee they will not strike uncooperative objects.
Understandably.
This is where the source material highlights the ASTM F3422 guidelines, which govern detect and avoid systems, commonly referred to as DAA.
Detect and avoid. The system responsible for ensuring the drone doesn't become a highly kinetic, unguided missile.
The ASTM F3422 standard approaches collision avoidance through intense mathematical modeling. The system first establishes what is known as position, space, and time spoofing verification, ensuring the drone isn't being tricked about where the obstacles are.
Right.
But the core of the avoidance mechanism relies on the GNC system continuously calculating what is called a near midair collision volume, or NMAC volume.
An NMAC volume. Let's visualize the variables of this for the listener, because it's not just a simple proximity alarm.
Imagine a mathematical force field, shaped roughly like an asymmetrical bubble or a cylinder, dynamically projecting outward from the center of the drone in real time.
An invisible computational personal space bubble protecting the aircraft.
Exactly. But the dimensions of this force field are not static. The EKF2 algorithm dynamically stretches, warps, and elongates the bubble based on complex kinematics.
Like what?
It factors in the drone's current airspeed, its mass, its maximum turning radius, and its current trajectory vector. If the drone is flying at high speed, the bubble stretches far out in front of it to account for braking distance.
While the bubble is stretching and morphing, the drone's LiDAR, millimeter wave radar, and optical cameras are aggressively scanning the surrounding airspace.
If an uncooperative object, a flock of birds, an unregistered hobby drone, or a manned aircraft flying without an active transponder breaches the outer warning layer of this mathematical bubble.
The drone has to react. But this is the critical juncture. There is no human operator holding a joystick, staring at a monitor, ready to swerve. The drone is flying autonomously.
The GNC system assumes total authoritative control. The goal is to maintain what the guidelines define as a well-clear distance.
How fast can it calculate that?
In a fraction of a millisecond, the algorithm calculates the closure rate and trajectory of the incoming threat. It instantly models dozens of potential escape trajectories in three-dimensional space.
And it just picks the best one.
It evaluates these paths, selects a specific maneuver that guarantees the well-clear distance while expending the least amount of battery energy and avoiding aerodynamic stall, and executes the physical maneuver.
It is actively predicting the future physical locations of chaotic objects around it and mathematically threading its way through them in the dark, entirely without human input.
And if we extrapolate the implications of a system capable of this level of dynamic, autonomous avoidance, we arrive at the absolute holy grail of the commercial and military drone industry, BVLOS.
Beyond visual line of sight.
Currently, the vast majority of aviation regulations mandate that a human pilot must maintain physical visual contact with a drone to visually guarantee it doesn't hit anything.
Which severely limits the utility of the technology.
Exactly. But if you possess a GNC system that is mathematically proven to detect incoming threats, calculate escape vectors, and autonomously dodge collisions exponentially faster and more accurately than human optical nerves and motor reflexes ever could.
You completely dismantle the regulatory argument for needing a human in the loop.
Yes, you do.
You can legally and safely launch these machines to fly hundreds of miles away, autonomously inspecting critical oil pipelines, delivering emergency medical supplies to remote areas, or executing complex maneuvers in hostile airspace, knowing the machine will protect itself better than a human ever could.
The machine evolves from a remotely piloted tool into a fully independent, self-preserving agent operating safely within the shared airspace.
The sheer density of the engineering we have unpacked today is staggering. When you step back and look at the holistic architecture of a modern UAV GNC system, it is fundamentally distinct from just a computer spinning propellers.
It's an entirely different beast.
It is a profoundly paranoid, self-healing, high-speed democracy of dissimilar microprocessors. It is a system engineered to constantly cross-examine the validity of its own physical senses, capable of recognizing when it is being mathematically deceived by a freezing gyroscope or a flooded barometer, and ruthlessly isolating that bad data.
And it does all of this on its own.
It physically heats its own inner ear to survive atmospheric extremes, builds its own internal reality using lasers, and the visual texture of the Earth when the satellite network is blinded, and dynamically projects mathematical force fields to dodge invisible collisions in the dark.
It represents the absolute pinnacle of resilient systems engineering. The entire architecture is built on the fundamental assumption that the environment is actively, maliciously attempting to destroy the machine, and it is mathematically designed to survive anyway.
Which leads directly to a final, somewhat uncomfortable thought to leave you, the listener, with today. In our broader public discourse, we spend an enormous amount of time and anxiety worrying about autonomous systems and artificial intelligence making catastrophic mistakes.
We do.
We worry about self-driving algorithms hallucinating or machines failing in unpredictable ways. But when you look at the granular reality of this technology, the extreme multi-layered hardware redundancy, the dissimilar silicon architectures voting in microseconds, and the ruthless mathematical trust filters actively managing sensory hallucinations.
The layers of fail-safes and self-diagnosis far exceed the biological capabilities of any human pilot.
Which forces us to ask the provocative question that will define the next era of aerospace. At what point do these paranoid, self-diagnosing, self-healing systems become mathematically more reliable and fundamentally more trustworthy in a high-stress crisis than a human pilot's own organic brain and easily disoriented senses?
It's a tough question to answer.
When you were blindfolded on that roller coaster, plummeting through a blizzard, who do you actually want threading the needle? The biological human who is freezing, terrified, and prone to vertigo? Or the paranoid, triple redundant machine that never blinks, never panics, and calculates the future in milliseconds?
It is a paradigm shift that challenges our inherent trust in human intuition over mathematical certainty.
Something to seriously consider as these machines fill the skies above us. Until next time, keep diving deep into the sources.